Hey QE Decoders, Michael L. Perry here. Today I want to talk about 4 different concurrency models. 3 of them you might have heard of, one of them you probably use all the time, and then the 4th one I'd like to contrast with those. So let's start things off with the pessimistic concurrency model. So for this, let's bring in Alice and Bob. And Alice and Bob need to share some common resource. So for this one, we just want to say that they need to read a version of that resource and then write back some changes. Okay? So Alice is going to go first. She's going to read version 1, and she wants to make some changes, so she's going to say, I need to lock that resource. Meanwhile, Bob is going to read version 1 as well, and if Bob wants to make some changes, he can't because he tries to lock. The resource is already locked. No changes allowed for him. Then, when Alice is done, she will write version 2a and unlock the resource. And now, if Bob tries to lock the resource to make a change, then he'll see immediately that there's a new version, 2a, and so he'll get 2a, make his changes, we'll call them 3b, and he'll write those back. So that's the pessimistic concurrency model. Pessimistic concurrency allows only one person to possibly be making a change at any given time because it locks the shared resource. So now let's take a look at optimistic concurrency. So again, we've got Alice and Bob and our shared resource. So Alice and Bob both read version 1, and now Alice wants to make her change. So she keeps track of the fact that her change to A has a predecessor of version 1. Version 1 was current at the time she made her change. And so she writes that to the shared resource, and the shared resource sees, hey, I've already got version 1, so I will accept the change from 1 to 2a. And now it's got version 2a as the current one. Meanwhile, Bob wants to make his change. Now he doesn't know that Alice has made her change, so he still thinks that version 1 is current. He makes his change to b, and then he tries to write that to the server. Now, the shared resource knows that 2a is current, but it sees that Bob wants to make a change from 1 to 2b. Since 1 doesn't match the current version, it's going to reject his change. And then Bob can read 2a, make his change 3b, and write that back. It allows different people to make changes at the same time, but it'll only accept the first one. So we can sometimes call this the first one wins. Let's compare that with the third concurrency strategy I want to talk about, last one wins. And this is the one that you've probably implemented most of the time because it's the one you implement by default. And so in this one, Alice and Bob have a shared resource. They both read version 1. And now Alice makes a change, so she writes version 2a to the shared resource. Bob wants to make a change, so he writes version 2b. Now, Bob never saw 2a, so those changes just get overridden, and they will never appear in the history again. That's what happens by default whenever you use a relational database and you just update a row. So these are the 3 concurrency strategies that you're probably most familiar with: optimistic, pessimistic, and last one wins. Now, I would like to contrast those with the historical concurrency model. So in the historical model, we're keeping track of the various predecessor relationships. So both Alice and Bob read version 1. Alice writes version 2a with the predecessor of 1. Bob writes version 2b with the predecessor of 1. Both changes are accepted. That's the important difference. There's no locking going on, so we're not preventing Bob from making any changes. And we're not rejecting his changes just because we've seen that Alice beat him to the punch. Also, we're not overwriting Alice's changes. We're keeping both of those versions, 2a and 2b. Now, at some point in the future, we can take a look at the shared resource. We can see that this tree of versions has forked, and we can see that it's got 2 leaves. 2 leaves means 2 candidate versions, and that means there's been a conflict. So that's what a historical model will do for you. It gives you a concurrency strategy that allows you to detect conflicts at some point in the future. You don't have to lock things, you don't have to reject anything. Because of this feature, historical modeling is the only one of these concurrency strategies that does not require a central server. If you want to have pessimistic concurrency, you need a central location to keep track of your locks. If you want optimistic, then there has to be a current version at some central location that can reject a change. And if it's the last one wins, then you're just overwriting a central storage for that row. But in the case of historical modeling, we can keep track of these in different histories over time, over a long period of time. And it's only after they come back together can we look and see at some point in the past, hey, there was a conflict. And now we can see what all the candidate values are, and we can resolve that conflict. There's another property that's really going to help us to create distributed systems like this, and that's the property of idempotency. So come on back next time, and we'll talk about that.